Hey.
Thanks so much. Um, I think first off, it's a slight change of topic, but I think it's going to be a fascinating set of talks, which are all very complementary. I wanted to kick off by just acknowledging a whole range of different co-authors here and funding agencies, but particularly in this talk, Richie Robertson from University of West Indies, who's made this fieldwork possible, and it builds on work done by a number of other people. So I'm going to talk about lahars. I'll explain what lahars are if you don't already know, and some of the hazards and sediment fluxes that relate to them and why we think they're important. Um, and I guess over the past few years, I've been working on a number of different volcanoes, subaerial, but particularly submarine. And most of the world's volcanoes lie in the ocean. About three-quarters of the world's volcanoes lie under the sea. And eruptions like this is the Hunga, or formerly known as Hunga Tonga Hunga Hapai eruption in 2022, which represented a VEI, so volcanic explosivity index, between about 5 and 6 eruption. This was the day before, and this has been a fascinating eruption because it created a huge eruption column up to about 57 kilometers high. It exploded about 6 to 7 cubic kilometers of sediment, of volcanic rock and material into the air, and most of that came down and plunged vertically or near vertically into the ocean. And created what we refer to as volcaniclastic density currents. And these are almost like pyroclastic flows that enter the ocean, mix with seawater, and create these turbidity currents, similar to those that you see off the Cascadia margin, but probably bigger volume, and running radially around the volcano. And in this case, in 2020, it ran over two of the cables, the only international cable on the seafloor that connects Tonga to the rest of the world, and cut it off from internet, or global internet and financial trading at a really, really critical time. And we actually know a reasonable amount about volcanic eruptions that enter the ocean, from pyroclastic density currents that have happened offshore Montserrat in the Caribbean. I know Seb is going to talk a bit about volcanic flank collapses, which, similarly to the Cascadia megathrust earthquakes, are very, very rarely observed, but could have very significant impacts. And events like the column collapse or fountaining that entered the ocean at Hunga volcano in Tonga in 2022. And these produce, in some cases, very long run out and fast volcaniclastic density currents that can move for hundreds or thousands of kilometers. And in the case of Hunga volcano, about, we think up to about 122 kilometers an hour. Um, so these are big volumes of sediment delivered to the ocean periodically during these eruptions that might happen every few hundred or thousands of years. So very important in terms of sediment fluxes into the ocean, important in terms of hazards because they can also trigger tsunami, which can impact coastal communities, but they're relatively rare. In this talk, I want to talk about lahars, so another type of volcaniclastic density current, if you like. These are concentrated and fast-moving flows, in some cases slurries of volcanic sediment that's mixed with water. There's a photo of one in St. Vincent taken by Jenny Barclay and Jeremy Phillips after the eruption of La Soufrière volcano in May 2021. So this is about a month after the climax of that eruption, which was a VEI 4 eruption. And these can generate these very fast-moving flows of sediment, in some cases with the consistency of wet concrete. They can be extremely hazardous, in fact, account for most of the recorded fatalities associated with any sort of volcanic hazard, and create some of the largest volume sediment flows on our planet. The right-hand plot shows sediment yields associated with mountainous rivers. And then when we look at the influence that lahars has, they can create orders of magnitude greater sediment fluxes along the catchments of these rivers as a result of ash and pyroclastic material that clogs up valleys and gets washed down the rivers. And in some cases, in the case of Ruapehu in New Zealand, the run out was more than 250 kilometers. And these turn out to be a global process. And in many cases, lahars reach the ocean. And this is due to a number of reasons. About 50% of subaerial arc volcanoes lie within about 20 kilometers of the coast. So because the run out of these flows can be long, they often reach the coastline. And we think they regularly reach the coastline, unlike pyroclastic density currents formed by the eruption of the Soufrière Hills volcano in Montserrat, or those generated by Hunga volcano. Lahars can happen months, years, or even decades after a volcanic eruption, when heavy rainfall or other processes can remobilize pyroclastic material that can be transported in the form of a lahar. And so all of these numbers shown here on this map, the red stars represent mapped subaerial volcanoes. Just for context, the global network of fiber optic cables on the seafloor is also shown. But the numbered locations here represent places where we know lahars reach the coastline. The interesting thing is, to date, there haven't been any studies that have looked at what happens beyond the coastline. So what happens when lahars actually enter the ocean? We only have a handful of studies that look at what happens when pyroclastic flows do this, but seemingly a big knowledge gap with regards to lahars entering the ocean. So we have an existing process-based model, which is developed pretty much on Jökulhlaup, so glacial lake outbursts, particularly in Iceland. There's a nice photo here showing what happens when sediment-laden flows reach the ocean. They create these surface plumes and plunge directly into the ocean. So in this sort of model, we have an outburst flood or heavy rainfall, which triggers a very high concentration sediment flow as a lahar. Where that reaches the ocean, it has a much higher density than the ambient seawater. It plunges in what we call a hyperpycnal flow and then triggers a sediment density current or turbidity current, which could travel for tens or hundreds of kilometers. So in this existing conceptual model, there's a direct connection between land and the deep sea. You'd see immediate impacts on seafloor infrastructure like telecommunications cables or fisheries. And the offshore sediment transport signal should look very, very similar to the onshore hydrograph signal, suggesting a very effective transfer of sediment from land to the deep sea. So if this model holds, as I said, we should expect to see temporally immediate connections and hazards that are quite synchronous with the lahars on land. Very effective transfer of particulate material, so volcanic ash, which can be toxic to offshore ecosystems, as well as carbon and other material carried in the flow. And theoretically, the deposit should enable us to reconstruct lahar events that have happened on land. And that's indeed the model proposed by Thierry Mulder and others in 2003, where if you turn your grain size profile for your deposits 90 degrees, it should broadly match the river flood hydrograph. So we'd like to test that, but the challenge is we haven't got any real-world observations to date offshore. So it's been challenging to see whether we can match this model or not. So that's what we're aiming to do with some initial results here. We want to ask what happens when do lahars reach the ocean? How do they behave when they get there? And what does this actually mean in terms of particulate fluxes and hazards? So the study area we're going to focus on is La Soufrière, a volcano on St. Vincent, where lahars occurred after the climactic eruption in April 2021. Lahars were detected on land by a seismic network and by river gauges and eyewitness observations. And rain gauges here show that when there's more than 20 mil rainfall in a day, you can get lahars, and they can occur across multiple different catchments synchronously. And lahars caused major damage, about 12 million US dollars total damage to roads, which are important, that connect remote fishing communities around the edge of the island in the west, the east, and the north, to bridges, houses, and other infrastructure. And during a period of about 8 months after the eruption, as the bottom left plot shows, the vertical orange and red lines represent places or timings when there were lahars. And in the case of the red ones, lahars occurred in all of the catchments around the volcano. So whilst there were 25 episodes of lahars, this could be many hundreds of lahars in total along these different catchments. What we've discovered, though, since then is that there have been significant impacts, not just onshore, but offshore. The top left plot here, these dashed black lines here represent fiber optic telecommunication cables that lie on the seafloor into water depths of about 1,700 meters. And here, just in excess of 55 kilometers worth of fiber optic cable was either damaged or buried by lahars or sediment remobilized by lahars, which moved, in some cases, more than 20 kilometers offshore. We see evidence of purse seine fisheries which have been destroyed by the effects of lahars which have plunged or moved into the ocean. An important turtle nesting beach shown as an orange star was destroyed. Diver photographs here in relatively shallow waters. This is off the west coast in 30 meters water depth. We see evidence of kind of this abrupt grain size change on the sea floor, which appears to be the front of a granular debris flow. And in 600 meters water depth, we see material transported from the shelf. These are limestone boulders, vegetation debris that came from on land, and linear striations, which are oriented downslope. And the damage to fishing has been significant. The damage to cables reaches the millions of dollars. So actually the impacts offshore in some cases may be even greater than those that have occurred offshore. So we see evidence of major subsea sediment transport as a result of lahars, but we don't really know how we draw the links between when they started and how they got here. So we use numerical models. This is work by Jeremy Phillips at Bristol University, which uses the lahar flow model, which accounts for erosion, deposition, and a change in the substrate. And here we could see by a lahar which starts in a river called the Overland River, so that is on the east coast of St. Vincent. We see that this flow started initially. If we look at the orange, this is the cumulative solids mass. It rapidly increased in volume, and then it progressively increased a little bit more. So it seems to match the signal of the river flood hydrograph. But within just a few kilometers, we can actually see that signal is quite different at station D. We can also see that the amount of sediment that is being transported is an order of magnitude greater or thereabouts. And so this is explained by these flows having eroded from the river. They've increased their volume, potentially in terms of the sediment, by an order of magnitude. And that ultimately then reaches the ocean. We don't quite know what happens there next. So in this presentation, I'll focus next on the Wallaby River. So this is the Overland River, a relatively small catchment, typical of many of the rivers around St. Vincent that reach the ocean. But the Wallaby River is a bigger river. And this is an area where there's relatively limited cloud cover, so we've been able to look at satellite data. And here, this is work by Lewis Bailey at Calgary University. He's been able to use an algorithm that basically quantifies the amount of sea surface turbidity, so how much sediment is on the sea surface, based on satellite images. And so here we could see that the greens, the kind of the hotter colors here, represent more sediment. So offshore the Wallaby River, coincident with lahars, we see these plumes of sediment. Material is clearly being conveyed offshore. 2 days later, it's more diffuse. 18 days later, however, there's a totally new plume that doesn't relate to a recorded lahar. 20 days later, a totally new one. And so we see that they're not necessarily synchronous with onshore lahar events. So Lewis has taken a point 100 meters offshore from the Wallaby River and looked at time series of the sea surface turbidity. And these are data from 2016 to before the eruption. And we can see generally very, very low levels of sea surface turbidity. But when we look after the eruption, we can see that there are massively higher peaks in sea surface turbidity. Some of these coincident with these intense rainfall peaks where there were recorded lahars offshore, but many of these between. So we can see there's a lag in terms of days or weeks after an onshore lahar event. And even continuing up to the present day, these represent time series that include all the way up to the end of last year. Sea surface turbidity is remarkably elevated, even 4 years after the initial eruption. So the effects of lahar-driven sediment offshore can still be very pronounced a long time after. What explains those delays? Well, we see the build-out of deltas in the top left. This is the Wallaby Delta here. It was built out with pyroclastic material as a result of lahars. A few days later, that collapsed into the ocean. So we think periodically material makes it to the coast, it builds out, it becomes unstable, and then it slumps. And the bottom left image is an extract from a video where we could see this slumping creating some of these sea surface plumes that we see from the satellite data. So in contrast to the existing model, we're seeing this cascade of hazards rather than a temporal coincidence of sediment being flushed offshore. And indeed, we see this in many other places where lahars reach the ocean. We see progradational deltas off the Belém River in Montserrat that are even bigger, and periodically we see bite marks happening back from collapses. Seb's been doing some nice work on Chaitén, as have others, and we could see a build out of this delta, which actually was a river that avulsed straight through a town. And periodically it grows, but it maybe cuts back a bit. So we think this is a common model, and we don't think this top model, the existing conceptual model, is wrong. It certainly probably holds for outburst floods and Jokkelhalps, but probably the bottom part of these more complex and cascading processes is more likely and more common, particularly in the months to years to decades after an eruption. So we conclude that we think actually transfers more likely pulse and piecemeal to the ocean rather than sudden and episodic. This means transfer to the deep sea is lagged in time, and hazards and ocean fluxes can happen over much longer timeframes, and reconstruction of individual lahar events from deposits could be really, really challenging. We think this is changing as a result of climate change, and some places like St. Vincent are becoming more rainy, so lahar events could become more extreme. And because we're seeing this as a global phenomenon, we think the amount of sediment being delivered to the world's oceans is not currently accounted for in current global budgets, and we do need to include that in future. The implications, well, for hazard, this is pretty clear, particularly as we're increasingly reliant on cables and the blue economy. Fisheries are already under impact as a result of climate change. And we should probably start thinking about the role of lahars in driving sediment, ash, carbon, and other material to the ocean, particularly in the context of biogeochemical cycling. So that is me.